300 million years. That is how long it took after the Big Bang for the first massive galaxies to appear. Not according to observation, according to physics, according to every model, every simulation, every piece of theory we had built over decades of careful work. 300 million years minimum. More realistically, 500 million to a billion. The universe needed time. Time for the first stars to ignite. Time for those stars to die and enrich the gas around them with heavy elements. Time for gravity to pull matter together into larger and larger structures. Then in July 2022, the James Webb Space Telescope opened its infrared eye and looked deeper into the past than any instrument in history. What it found broke everything. Galaxies. Massive, mature, fully formed galaxies shining brilliantly just 200 million years after the Big Bang. Galaxies containing billions of stars in a universe barely old enough to have formed stars at all. Galaxies sitting in an epoch of cosmic time that every physicist on Earth said should still be dark, empty, waiting. The numbers didn't add up. The timeline didn't work. The physics didn't allow it. Scientists stared at the data, ran the measurements again, checked for errors, and came back with the same impossible answer. These galaxies exist, and buried beneath that impossible discovery is a question that cuts to the foundation of everything we think we know about the universe. If the cosmos built galaxies this early, this fast, this massive, what else is wrong about the story we've been telling? What other assumptions are crumbling under the weight of real observation? In this video, we're going to take you through the discovery that has cosmologists rewriting textbooks, the specific galaxies that shattered expectations, the physics that said they were impossible, how scientists are fighting to explain what Webb found, and what it means when the universe refuses to follow the rules we thought governed all of existence. If you enjoy the journey, hit like and subscribe so you never miss what we find next. Now, take a breath. We're going back to the beginning of everything. Picture nothing, not empty space, not darkness. True nothing, no space, no time, no matter, no energy. A mathematical point of infinite density and infinite temperature, containing everything that would ever exist, compressed into a volume smaller than an atom. Then it exploded. 13.8 billion years ago, the universe began. Not as an explosion into space, but as the explosive creation of space itself. The Big Bang was not an event happening somewhere. It was the birth of everywhere. In the first trillionth of a second, the universe expanded faster than light, not through space. Space itself was stretching, inflating, growing from nothing into something at a rate that defies human intuition. Within the first 3 minutes, the temperature dropped enough for the first atomic nuclei to form. Hydrogen, helium, trace amounts of lithium, the fundamental building blocks. For the next 380,000 years, the universe was a glowing fog. Matter and radiation so tightly coupled that light couldn't travel freely. Photons scattered endlessly off electrons in an opaque plasma that filled all of existence. Then came recombination. The universe cooled enough for electrons to bind with nuclei, forming the first neutral atoms. Light was suddenly free to travel. The fog lifted. The universe became transparent for the first time. That moment left behind a signature we can still detect today. The cosmic microwave background radiation. A faint glow visible in every direction. The oldest light in the universe. A baby picture of the cosmos at 380,000 years old. This is confirmed. The cosmic microwave background has been mapped in exquisite detail by satellites like COBE, WMAP, and Planck, giving us a precise snapshot of the universe's structure at recombination. After recombination came the Dark Ages, not because something was wrong, because nothing was shining yet. The universe was filled with hydrogen gas drifting through expanding space, cooling slowly, waiting for gravity to do its work. No stars, no galaxies, no light except the fading glow of the Big Bang itself, stretching into longer and longer wavelengths as space expanded. For 100, perhaps 200 million years, The universe was truly dark, but gravity never stops. Even during the Dark Ages, tiny variations in density, microscopic fluctuations imprinted during the first moments of the Big Bang, were growing. Regions slightly denser than average pulled in more matter. Those regions grew denser still. Positive feedback. Dark matter, invisible matter, that doesn't interact with light, but feels gravity, clumped together first. It formed gravitational wells, halos of mass pulling normal matter inward. Hydrogen gas fell into those dark matter halos. As it fell, it compressed. As it compressed, it heated. Pressure built, temperature rose, and eventually, somewhere in the universe, in the densest core of a collapsing gas cloud, the temperature and pressure crossed a threshold. Hydrogen atoms began fusing into helium. The first star ignited. We don't know exactly when this happened. Current models place it somewhere between 100 and 200 million years after the Big Bang. We don't know what the first star looked like. Theoretical models suggest it was massive, perhaps hundreds of times the mass of our Sun, burning ferociously and living only a few million years before exploding. That explosion, that first supernova, changed everything. It scattered heavy elements into the surrounding gas. Carbon, oxygen, nitrogen, iron, elements forged in the core of that dying star, released in a violent death that seeded the cosmos with the raw materials for everything that would come after. From that enriched gas, the next generation of stars formed, smaller, cooler, longer lived. And around those stars, structures began to assemble. The first galaxies, tiny by today's standards. A few million stars clustered together, bound by gravity, shining weakly in the darkness. This process, according to every simulation, every physical model, every extrapolation from observations of the later universe, took time, hundreds of millions of years. You couldn't rush it. Gravity works at the speed it works. Gas collapses at the rate physics allows. Stars form, burn, die, and enrich their surroundings on timescales dictated by nuclear fusion and thermodynamics. The models were clear. Small proto-galaxies might appear by 200 to 300 million years after the Big Bang. Larger galaxies, systems with tens of millions of stars, wouldn't emerge until 500 million years. Galaxies comparable in mass to the Milky Way wouldn't fully assemble until 1 billion years or more. That timeline wasn't speculation. It was built on decades of observational data from Hubble, from ground-based telescopes, from studying how galaxies grow and evolve in the nearby universe, and working backward. Lambda-CDM, the standard model of cosmology, predicted this timeline with confidence. Lambda refers to dark energy, the mysterious force accelerating the universe's expansion. CDM stands for cold, dark matter, the invisible scaffolding around which galaxies form. Lambda-CDM explains the cosmic microwave background. It explains the large-scale structure of galaxy clusters. It explains the abundances of light elements. It has been tested against observation after observation and passed every test, until Webb looked at the early universe. August 2026. The James Webb Space Telescope had been operational for just weeks. The first deep field images were being processed. Astronomers around the world were seeing the earliest data releases, learning how to work with Webb's infrared detectors, calibrating, checking, exploring what this new instrument could do. One of Webb's first targets was a small patch of sky that Hubble had photographed before. A deep field designed to test the telescope's capabilities. The image came back. Thousands of galaxies filled the frame, scattered across the black background of space like jewels on velvet. That alone was expected. Hubble had seen thousands of galaxies in deep exposures, but among those thousands were objects that didn't make sense. They were bright, far brighter than objects at their apparent distance should be, and their colors were wrong. Extremely red in the infrared, invisible in shorter wavelengths. Astronomers measure distance using redshift. As the universe expands, light traveling through space gets stretched. The wavelength increases. Blue light shifts toward red. Red light shifts into the infrared. The amount of shift tells you how far the light has traveled, which tells you how far back in time you're looking. These strange red objects had redshifts unlike anything Hubble had routinely detected. Redshifts of 10, 12, some candidates pushing towards 16 or higher. For context, a redshift of 10 corresponds to a universe just 480 million years old. Redshift 12 means 370 million years. Redshift 16 would place a galaxy at roughly 250 million years after the Big Bang. At those epochs, we expected faint smudges, tiny proto-galaxies just beginning to coalesce. What Webb found were monsters, galaxies glowing with the light of billions of stars. Massive structures that looked mature, organized, fully assembled. The research teams checked their measurements, ran the analysis again, looked for errors. The data held. Dr. Ivo Labbé, an astronomer at Swinburne University of Technology in Australia, was part of one of the teams analyzing the early data. His reaction, shared later in interviews, was simple. "We just looked at each other and said, 'This can't be right,' but it was right. This is confirmed." Multiple independent research groups analyzing Webb's first deep field observations reported galaxy candidates at redshifts between 10 and 16, corresponding to the universe at 200 to 500 million years old, with brightnesses implying stellar masses far exceeding Lambda-CDM predictions. The first galaxy to truly shock the community was catalogued as Glass Z13, a brilliant red dot in Webb's infrared images. When the team carefully measured its brightness across multiple wavelengths, the redshift came back at 13.1. That places Glass Z13 in the universe at just 325 million years old, and it wasn't faint. It was bright enough to suggest it contained roughly 1 billion solar masses worth of stars. 1 billion stars. Already formed, already shining. In a universe barely 1/3 of 1 billion years old, the math didn't work. To form 1 billion solar masses of stars, you need several things. First, a dark matter halo massive enough to gravitationally capture at least 10 billion solar masses of gas. Star formation is inefficient, only a fraction of available gas turns into stars. Second, time for that gas to cool. Hot gas has pressure that resists gravitational collapse. It has to radiate away energy before it can condense. Third, time for stars to actually form. Even massive stars take a few million years to collapse from a gas cloud and ignite fusion. Fourth, if the galaxy shows heavy element enrichment, which spectroscopy would later reveal some of these do, time for earlier generations of stars to die and release those elements. Add it up, even under the most optimistic assumptions, and you're looking at a minimum timeline of several 100 million years from the first dark matter halo forming to a mature galaxy with 1 billion solar masses. The universe at the time we're observing Glass Z13 is only 325 million years old. Subtract the Dark Ages, the period before any stars existed, and you have maybe 150 to 200 million years of usable time. The timeline is impossible. Glass Z13 was not alone. A galaxy designated Glass Z11 at redshift 11.6 appeared even brighter. Its stellar mass estimate pushed toward 1.5 billion solar masses at just 400 million years. Then came the real bombshell, a galaxy initially catalogued as CERS 93316, later analyzed and reported with a photometric redshift of 16.7. If that measurement holds, it places this galaxy just 235 million years after the Big Bang. 235 million years. The universe at that point had barely cooled from its initial fireball. The Dark Ages had only just ended. The first stars had ignited perhaps 50 to 100 million years earlier, and here was a galaxy, massive, bright, structured, Dr. Rohan Naidu of the Harvard-Smithsonian Center for Astrophysics, part of the team studying these objects, described the situation bluntly. "We're seeing things we didn't think we'd see for another year or two of Webb operations, and they're showing up immediately." As more data came in from different Webb surveys, JADES, SEERS, GLASS, NG Deep, the pattern repeated. Everywhere Webb looked deep enough to see the early universe, it found massive galaxies. Not one or two statistical flukes. Dozens of them. And the more carefully teams analyzed their brightness, colors, and structure, the worse the problem became. These weren't just early galaxies forming a bit faster than expected. These were galaxies with stellar masses comparable to the Milky Way today, sitting in a universe less than 5% of its current age. One galaxy, GS 9209, observed at redshift 4.66, about 1.25 billion years after the Big Bang, wasn't just massive, it was quiescent. It had stopped forming stars. Spectroscopic analysis showed it contained old stars that had formed hundreds of millions of years earlier and had been aging passively ever since. For a galaxy to be quiescent at 1.25 billion years after the Big Bang, it has to have formed all its stars, exhausted or expelled its gas supply, and settled into old age by that point. That pushes star formation back into the first 500 to 700 million years of cosmic history. Dr. Adam Carnell of the University of Edinburgh, who led the study of GS 9209, called it the most massive quiescent galaxy we've ever seen at this epoch. "It's challenging everything we thought we knew," he said. "This is confirmed. GS 9209 is a spectroscopically confirmed quiescent galaxy at redshift 4.66, with a stellar mass of approximately 40 billion solar masses and stellar population, ages indicating formation well within the first billion years of the universe." The astronomical community responded the way scientists always do when faced with data that contradicts theory. First, disbelief. Surely the measurements are wrong. Then, careful rechecking. Are the redshifts accurate? Could these be lower redshift dusty galaxies masquerading as high redshift objects? Then, alternative explanations. Could something about the physics be different in ways we haven't accounted for? And finally, when all else fails, acceptance and adaptation. We're currently somewhere between rechecking and alternative explanations. Some researchers remain cautiously hopeful that many of these candidates will turn out to be misidentified, that spectroscopic follow-up will reveal they're actually at lower redshifts. Others have moved on to proposing modifications to the standard model. The problem is specific and quantifiable. In Lambda-CDM, structure forms hierarchically. Small dark matter halos collapse first. Gas falls into those halos. Stars form. Small galaxies merge into larger ones over billions of years. The timeline for this process is set by the physics of gravitational collapse, the cooling rate of gas, and the efficiency of star formation. Run the simulations with standard assumptions, and massive galaxies don't appear until 500 million to a billion years after the Big Bang. Webb is finding them at 235 million years. Dr. Michael Boylan-Colchin, an astrophysicist at the University of Texas at Austin, ran detailed simulations comparing Webb's observations to Lambda-CDM predictions. His results were stark. To fit the observed galaxy masses, star formation efficiency would have to approach 100%. That means every single hydrogen atom falling into these galaxies turns into a star. No waste, no gas expelled by supernova explosions, no gas consumed by black holes. Perfect conversion. That doesn't happen. It's never been observed in any galaxy anywhere in the universe. Typical star formation efficiency in galaxies is 10% to 30%. Most gas gets heated by stellar feedback supernovae, stellar winds, radiation from young stars, and blown out before it can form stars. 100% efficiency isn't just unlikely, it's physically implausible. And yet, that's what the models require to explain what Webb sees. This is the honest scientific assessment. The data from Webb is solid. The redshift estimates are robust for many objects, and reconciling the observations with Lambda-CDM requires either unprecedented star formation efficiency or modifications to fundamental aspects of cosmological theory. Let's talk about the specific physics that makes these galaxies so problematic. When gas falls into a dark matter halo, it heats up. Gravitational energy converts to thermal energy. The gas becomes hot. Hot gas has pressure. Pressure resists further collapse. For the gas to continue condensing into star-forming clouds, it has to radiate that heat away. The cooling rate is limited by atomic physics. Hydrogen and helium, the only elements available in the pristine early universe, are poor coolants. They radiate energy slowly. This cooling bottleneck is one of the fundamental constraints on star formation timescales. In the standard picture, efficient star formation required the buildup of heavy elements, carbon, oxygen, nitrogen, from earlier generations of stars. Those elements act as better coolants, allowing gas to shed heat faster. But producing heavy elements requires time. First-generation stars have to form, live, and explode before those elements exist. The galaxies Webb found don't have time for that process. Some of them, when analyzed spectroscopically, show evidence of already containing significant amounts of heavy elements. Oxygen has been detected in galaxies at redshift 11, 12, even higher. Oxygen forms inside stars and is released when those stars die. Its presence means at least one full generation of stars has already completed its life cycle. Dr. Pablo Arrabal Haro, a researcher at NSF's NOI lab studying one such galaxy, described finding oxygen at these epochs as shocking. We're seeing chemical enrichment that should take far longer to develop, he noted. The oxygen abundance isn't trace amounts. In some cases, it's comparable to what you'd find in galaxies 1 billion years old in the later universe. How does a galaxy enrich itself with heavy elements this fast? The only way is if star formation and stellar evolution proceeded at rates far faster than anything observed in the universe today. Massive stars, the ones that produce and release heavy elements when they explode, live only a few million years. But you need many generations of them, and you need time between generations for the gas to cool, mix, and collapse again. The timeline remains impossibly tight. One proposed solution involves population 3 stars, the hypothetical first generation of stars. In the complete absence of heavy elements, gas clouds in the early universe couldn't cool as efficiently. Inefficient cooling means the clouds stayed hotter and didn't fragment as much. That could lead to the formation of extremely massive stars, hundreds or even 1,000 times the mass of the Sun. Such stars would burn incredibly brightly, producing vast amounts of ultraviolet radiation. They'd die quickly, in just 1 million years or so, and they'd produce heavy elements very efficiently, enriching large volumes of gas with a single supernova. If the first stars were predominantly these supermassive objects, they could enrich the universe and trigger subsequent generations of star formation far faster than current models assume. The problem is, we've never observed a population 3 star. They're purely theoretical, and theoretical models suggest stars much above 300 solar masses are unstable. They might tear themselves apart before they can fully form. Even if they could exist, the total number would be limited. They die so fast that only a brief burst of POP3 star formation is possible before the gas is enriched, and normal stars start forming instead. Could that brief burst be enough to explain Webb's galaxies? It's possible, but it's speculative. This is the current scientific thinking, but it's not confirmed. Population 3 stars remain hypothetical, and whether they could form in sufficient numbers to solve the early galaxy problem is an open question. Another constraint comes from the Eddington limit. When stars form and begin shining, their light exerts outward pressure on the surrounding gas. Photons carry momentum, and when they interact with atoms, they push. If star formation is too rapid, if the galaxy becomes too luminous, radiation pressure can counteract gravity entirely. The gas stops collapsing. Star formation shuts down. This sets a maximum rate at which galaxies can grow. You can't violate the Eddington limit without violating fundamental physics. The massive early galaxies Webb found appear to be pushing right up against this limit, or possibly exceeding it. That shouldn't be possible. Yet another problem involves supernova feedback. When massive stars explode, they release enormous amounts of energy. That energy heats the gas around them to millions of degrees and drives powerful winds that blow gas out of the galaxy. Supernova feedback is one of the primary mechanisms regulating star formation. Without it, simulated galaxies turn all their gas into stars and become unrealistically massive. But if feedback is operating in these early galaxies, how are they forming stars so efficiently? The system should self-regulate. Rapid star formation leads to many massive stars. Those stars explode. The explosions heat and expel gas. Star formation slows. For these galaxies to exist, either feedback was somehow weaker in the early universe, which seems unlikely since supernova physics shouldn't change, or they were accreting gas faster than feedback could expel it. But that runs into the Eddington limit again. It's a closed loop. Every solution creates a new problem. Some researchers have proposed that dark matter itself might behave differently than assumed. Lambda-CDM assumes cold dark matter particles that move slowly and clump smoothly under gravity. What if dark matter has properties we haven't accounted for? What if it can self-interact, colliding with itself in ways that allow faster or more efficient halo formation? Self-interacting dark matter could potentially form denser cores in halos. Denser cores mean stronger gravity. Stronger gravity means more efficient gas accretion and star formation. There's no direct evidence for self-interacting dark matter, but the gap between observation and prediction is large enough that physicists are willing to consider it. Dr. Stacy McGarr of Case Western Reserve University, who has long argued that dark matter models face unresolved issues on small scales, noted that Webb's discoveries are forcing the field to take seriously alternatives that were previously dismissed. Then there's the question of whether the universe might be older than we think. The age of the universe, 13.8 billion years, is calculated from the expansion rate and the observed densities of matter and dark energy. If the universe were actually 15 or 16 billion years old, that would give an extra billion or two for these galaxies to form, potentially relieving some of the timeline pressure. The problem is, the universe's age isn't determined by a single measurement. It's constrained by multiple independent methods that all agree. The cosmic microwave background, measured by Planck, gives 13.8 billion years. The Hubble constant gives a consistent age when you extrapolate backward. The abundances of radioactive elements in the oldest stars provide an independent lower limit that also agrees. Changing the age requires breaking all those agreements simultaneously. That seems extraordinarily unlikely. So where does that leave cosmology? The honest answer is in a state of productive tension. Lambda-CDM is not being abandoned. It's been too successful in too many areas explaining the CMB, large-scale structure, element abundances, the accelerating expansion. But something about how we model the baryonic physics, the behavior of normal matter, gas cooling, star formation efficiency in the very early universe is clearly incomplete. Dr. Rachel Somerville of the Flatiron Institute, a leading expert on galaxy formation simulations, put it clearly. We're going to have to rewrite the textbooks on how galaxies formed in the first billion years. The universe is telling us something we didn't expect. This is confirmed. The emerging scientific consensus is that while Lambda-CDM remains the best framework, significant revisions are needed in how star formation, gas dynamics, and feedback processes are modeled in the extreme conditions of the early universe. Let's talk about the engineering miracle that made these discoveries possible. Because finding galaxies at redshift 10, 12, 16 required a telescope unlike anything ever built. The James Webb Space Telescope is the largest infrared observatory ever launched into space. Its primary mirror spans 6.5 meters 21 feet across, composed of 18 hexagonal segments coated in gold. Gold was chosen because it's the most reflective material at infrared wavelengths, where ancient redshifted light from the early universe now appears. The mirror was too large to fit inside any rocket, so it was designed to fold. The 18 segments were arranged in a pattern that could collapse during launch and unfold once in space. That deployment sequence involved over 300 single-point failures, over 300 steps where if one thing went wrong, the entire $10 billion mission would fail. It worked perfectly. Webb doesn't orbit Earth. It sits at the second Lagrange point, L2, about 1 million miles away in the direction opposite the Sun. At L2, gravitational forces from Earth and the Sun balance in a way that allows Webb to maintain a stable orbit with minimal fuel. More importantly, L2 keeps Webb in permanent shadow. A massive sun shield the size of a tennis court blocks heat from the Sun, Earth, and Moon, allowing the telescope to cool to nearly absolute zero. Webb's instruments operate at around 447 degrees Fahrenheit, just 50 degrees above absolute zero. That extreme cold is necessary because Webb observes in the infrared essentially heat radiation. If the telescope itself were warm, its own thermal glow would swamp the faint signals from distant galaxies. Cooling it to near absolute zero makes Webb sensitive enough to detect the warmth of a bumblebee on the Moon. This is confirmed. NASA designed Webb's thermal systems to maintain operating temperatures below 50 Kelvin for most instruments, with the mid-infrared instrument cooled even further to 7 Kelvin. Why infrared? Because of redshift. When the universe expands, it stretches light. Photons that started their journey in the ultraviolet or visible spectrum get stretched into the infrared by the time they reach us. The farther away the source, the more the light has been stretched. For galaxies at redshift 10 or higher, light emitted in visible wavelengths has been stretched so far that it now appears in the mid-infrared, at wavelengths between 3 and 30 micrometers. Hubble operates primarily in visible and near ultraviolet light. It can see into the near-infrared, but not far enough to catch the most distant galaxies. Webb was specifically designed to cover those wavelengths. Its instruments span from 0.6 micrometers, the red edge of visible light, all the way to 28 micrometers, deep in the mid-infrared. That spectral coverage is what allows Webb to see galaxies completely invisible to Hubble. When Hubble looked at the same fields Webb later observed, many regions appeared empty. Just black sky. Webb revealed those empty regions were full of galaxies. Ancient galaxies shining in infrared light. Hubble couldn't detect. They were always there. We just couldn't see them. Webb carries 4 primary science instruments. NIRCam, the near-infrared camera, captures wide-field images across multiple infrared wavelengths simultaneously. Most of the stunning deep-field images released by NASA came from NIRCam. NIRSpec, the near-infrared spectrograph, splits light into its component wavelengths, revealing the chemical composition of galaxies and allowing precise redshift measurements. MIRI, the mid-infrared instrument, extends Webb's vision further into the infrared, capturing the coolest and most redshifted objects. And NIRIS for specialized imaging and wide-field spectroscopy. Together, these instruments give Webb the ability not just to see distant galaxies, but to study them in detail. The first deep-field image from Webb was released on July 12, 2022. It showed a galaxy cluster called SMACS 0723. The cluster itself wasn't particularly special. What made the image stunning was everything beyond it. Thousands of galaxies scattered across the background, their light bent and magnified by the cluster's gravity, a phenomenon called gravitational lensing. Among those thousands were dozens of galaxies at redshifts higher than Hubble had ever routinely detected. Dr. Taston, Jane Rigby, Webb's senior project scientist at NASA, described the moment the data came in. "We knew it would be spectacular. We didn't realize it would be this immediate." Within weeks, papers were being published on galaxies at redshift 10, 11, 12. Within months, candidates above redshift 15 started appearing. One of Webb's key capabilities is multi-object spectroscopy. NIRSpec has a device called a microshutter array. Thousands of tiny shutters, each the width of a human hair, that can be individually opened or closed. This allows Webb to observe up to 200 objects simultaneously. You can take a deep field image, identify dozens of interesting galaxy candidates, and obtain spectra for all of them in one observation. That efficiency is what has allowed confirmation to happen so quickly. In previous eras, confirming the redshift of a single distant galaxy required an entire night on a major telescope dedicated to that one object. With Webb, you can confirm dozens per observation. The bottleneck isn't telescope time, it's how fast researchers can analyze the data. Another critical capability is sensitivity. Because Webb is in space and cooled to near absolute zero, its detectors have almost no thermal noise. Ground-based infrared telescopes fight the thermal glow of Earth's atmosphere, the telescope structure, and the instruments themselves. In space, that noise vanishes. Webb sees only the sky. The faintest galaxies in Webb's deep fields have brightnesses around 31st magnitude. That's roughly 10 billion times fainter than the faintest star visible to the naked eye under perfect conditions. Detecting something that faint requires collecting photons for hours, sometimes tens of hours, and counting every single one. Webb's detectors are sensitive enough to register individual photons arriving from galaxies billions of light years away. This is confirmed. Webb's instruments achieve sensitivities down to AB magnitude 31 in deep exposures, enabling detection of the faintest and most distant galaxies in the observable universe. The process of identifying high redshift galaxies begins with deep imaging. Webb points at a patch of sky and stares, collecting light for hours. The images are processed to remove cosmic rays, detector artifacts, and noise. Then algorithms scan the images looking for sources objects that stand out above the background. For each source, photometry is measured. How bright is it in each infrared filter? The pattern of brightness across wavelengths creates a spectral energy distribution, or SED. The shape of that SED gives clues about what you're looking at and provides a rough redshift estimate. Galaxies at very high redshift have a characteristic feature. They're invisible in bluer filters and suddenly appear in redder filters, creating a sharp dropout. That dropout happens because light blueward of the Lyman alpha line of hydrogen gets absorbed by neutral hydrogen in the intergalactic medium. The position of the dropout tells you the redshift. Once candidates are identified, spectroscopic follow-up confirms or refutes the estimate. A spectrum reveals precise wavelengths of emission lines, giving an exact redshift, and from the redshift, you calculate the galaxy's distance, the age of the universe when the light was emitted, and combined with brightness, the galaxy's intrinsic luminosity and stellar mass. Every step has uncertainties. But when all the pieces align, clean photometry, clear dropout, spectroscopic confirmation, you have a solid detection. And Webb has delivered dozens. Let's talk about specific galaxies. Galaxies 13 at redshift 13.1 was one of the first shocks. Roughly a billion solar masses at 325 million years after the Big Bang. Galaxies 11 at redshift 11.6, even brighter. Stellar mass pushing toward 1.5 billion suns. Then Maisie's galaxy, officially CE's 87369, at redshift 11.4, spectroscopically confirmed roughly 390 million years after the Big Bang. Maisie's galaxy showed strong emission lines from oxygen. Significant oxygen abundance, meaning substantial chemical enrichment, had already occurred. Dr. Stephen Finkelstein of the University of Texas at Austin, part of the team that discovered it, named it after his daughter. Finding something this significant, you want to mark the moment, he said. Then there's CEEAR's 93316, the galaxy with a photometric redshift of 16.7. If confirmed, it would be the earliest galaxy ever detected, sitting just 235 million years after the Big Bang. The measurement is still debated. Photometric redshifts at these extremes are uncertain. Spectroscopic confirmation requires more telescope time than has been allocated yet. Some researchers argue it might be at a lower redshift, perhaps around 5 or 6, which would still be early but not record-breaking. Others maintain the photometry is solid. The debate continues, but even if CE's 93316 turns out to be misidentified, there are dozens of other galaxies at redshift 10 to 13 where the data is more secure. The problem doesn't rest on one object, it rests on a population. Another galaxy worth highlighting is GS9 2009. At redshift 4.66, it's not at the extreme edge. It corresponds to about 1.25 billion years after the Big Bang, but GS9 209 is quiescent. It stopped forming stars. Spectroscopy shows it contains old red stars that formed hundreds of millions of years earlier. For a galaxy to be quiescent at 1.25 billion years, it must have completed its entire star-forming life cycle, exhausted its gas, and settled into passive aging by that epoch. That pushes active star formation back to within the first 500 to 700 million years. Dr. Adam Carnell, who led the study, called it astonishing. This galaxy has already lived a full life and retired while the universe is still in its infancy. As the data accumulated, researchers noticed something else troubling. These massive early galaxies aren't rare. If they were 1 in a million flukes, statistical outliers forming under extraordinarily unusual conditions, you could argue they don't challenge the overall model, but Webb is finding them everywhere it looks. In the JADIS survey, covering a relatively small patch of sky, researchers identified over 700 galaxies at redshifts between 7 and 12. Dozens of those are massive and luminous, far beyond what Lambda-CDM predicts should exist at those epochs. The number density, how many exist per unit volume of space, is orders of magnitude higher than simulations predicted. Dr. Brant Robertson of UC Santa Cruz, one of the JADIS leads, described it as an embarrassment of riches. Everywhere we point Webb, massive early galaxies appear. This isn't a handful of weird objects, it's a population. If the standard model were correct, these galaxies should be vanishingly rare at 300 to 500 million years after the Big Bang. Finding one would be surprising. Finding dozens in a survey covering a tiny fraction of the sky suggests they're common. That changes everything. It's not just that a few galaxies formed faster than expected, it's that galaxy formation as a whole proceeded differently than every model predicted. The early universe wasn't slowly assembling structure, it was exploding with it. This is the current scientific assessment. The abundance of massive galaxies at high redshift, not just their existence, represents a fundamental challenge to standard hierarchical galaxy formation models. Let's talk about what this means for cosmic history. For decades, the story we told went like this: the Big Bang, the Dark Ages, first stars igniting around 100 to 200 million years, small protogalaxies forming by 500 million years, those protogalaxies merging over billions of years into larger structures, massive galaxies like the Milky Way, not fully assembling until several billion years after the Big Bang. A slow, steady, hierarchical process. Bottom-up structure formation. That story is now in question. Webb is showing us massive galaxies when the universe was barely 2% of its current age. That suggests structure formation was top-heavy, not bottom-up. Large structures formed early, not late. The implications extend to something called the epoch of reionization. After the Dark Ages, as stars and galaxies formed, their ultraviolet radiation began ionizing the neutral hydrogen filling the universe. Ionized hydrogen is transparent to light. Neutral hydrogen absorbs it. The transition from a neutral to ionized universe is one of the major phase changes in cosmic history. We know reionization was complete by about 1 billion years after the Big Bang, but we didn't know when it started or how fast it progressed. The standard model assumed it was gradual, driven by small galaxies forming over hundreds of millions of years, their cumulative UV output slowly ionizing larger bubbles of space. If massive galaxies formed very early, they could have contributed far more ionizing radiation than expected. That would make reionization happen faster and earlier. Some of Webb's high redshift galaxies are being observed during the epoch of reionization itself, at redshifts between 7 and 12. Their spectra show absorption features indicating they're surrounded by partially neutral hydrogen. They're literally being observed in the act of ionizing their surroundings. By studying these galaxies, astronomers can map how reionization proceeded, which regions ionized first, and what sources provided most of the ionizing photons. Early results suggest massive galaxies played a larger role than models anticipated. If confirmed, that rewrites our understanding of one of the universe's major transitions. There's also the question of supermassive black holes. Almost every massive galaxy in the nearby universe contains a supermassive black hole at its center. The Milky Way's black hole is about 4 million solar masses. The most massive known exceed 10 billion. We don't fully understand how these black holes formed or grew so large. The leading theory is they started as small seed black holes, perhaps a few hundred solar masses, left when the first massive stars died. Those seeds grew by accreting gas and merging with other black holes over billions of years. But growing a billion solar mass black hole from 100 solar mass seed in less than a billion years is hard. Black hole growth is limited by the Eddington limit. Just like star formation, accrete too fast and radiation pressure blows away the infalling material. Webb has found active supermassive black holes quasars at redshifts above 10. These black holes already contain hundreds of millions to billions of solar masses, less than 500 million years after the Big Bang. The same timeline problem that applies to galaxies applies to black holes. How did they grow so massive so fast? One proposed solution is direct collapse black holes, seeds that started not at hundreds of solar masses, but at hundreds of thousands or millions. These could form if a massive gas cloud collapsed directly into a black hole, without fragmenting into stars first. That requires very specific conditions, pristine gas with almost no heavy elements, kept hot enough to avoid fragmentation. Whether those conditions existed widely enough to explain the abundance of early supermassive black holes remains uncertain. Let's step back and consider the philosophical implications. For decades, cosmology operated with certain assumptions about how the universe behaves. Structure forms slowly. The early universe is simple. Complexity emerges gradually over cosmic time. Those assumptions were grounded in theory and supported by observations from Hubble and other telescopes. They shaped how we thought about everything from galaxy formation to the conditions necessary for life. If the universe built massive galaxies immediately, if complexity emerged early rather than late, those assumptions are wrong. And if our assumptions about the early universe were wrong, what else might we be wrong about? The principle of mediocrity, the idea that Earth, our Sun, our galaxy are typical, not special, has guided astronomy for centuries. Webb's discoveries reinforce that principle in one sense. Galaxies are everywhere, forming under all kinds of conditions, even in the chaotic early universe. But in another sense, Webb is showing the universe is stranger and less predictable than mediocrity suggests. We thought we understood the rules. The universe is revealing. The rules are more complex than we imagined. Dr. Jane Rigby put it simply in a public lecture. Every time we've built a more powerful telescope, the universe has surprised us. Webb is no exception. If anything, it's surprising us faster and more dramatically than any previous mission. So where do we go from here? The first priority is confirmation. Many of the highest redshift candidates are still based on photometric redshifts estimates from the galaxy's colors across multiple filters. Photometric redshifts are powerful but imperfect. They can be wrong, especially at extreme redshifts where the spectral features are subtle. To truly confirm a galaxy's distance, you need spectroscopy. Webb's NIRSpec can obtain spectra of these faint objects, but it requires significant time. Each spectrum might need 10, 20, even 50 hours of exposure. Demand for Webb's time is enormous. Only about 20% of proposed observing programs are approved. High redshift galaxy spectroscopy is a priority, but it competes with exoplanet studies, solar system science, nearby galaxy observations, and dozens of other fields. The confirmation process is ongoing. As of 2025, spectroscopic confirmation exists for a handful of galaxies above redshift 10. Dozens more candidates await follow-up. Some will hold up. Some will turn out to be lower redshift objects whose colors mimicked high redshift dropouts. But even if half the candidates are eventually ruled out, the problem remains. Even 20 or 30 confirmed massive galaxies at redshift 10 or higher is 20 or 30 more than Lambda-CDM predicted. One confirmed galaxy that spectroscopically validated the early findings is JADES GSJ Sitten 0, redshift 13.2 confirmed. About 325 million years after the Big Bang, the spectrum shows emission lines from oxygen and hydrogen, confirming both the distance and the presence of heavy elements. Dr. Brant Robertson, part of the confirmation team, Describe the moment. This is real. This galaxy exists in the very early universe, and it's more massive than we thought physically possible. Another confirmed object is JADE's GS. Its spectrum revealed extremely strong emission lines, far more intense than typical galaxies. That suggests rapid, intense star formation in a compact region, possibly fueled by gas streaming into the galaxy at high rates. It also shows low heavy element abundance, about 2% of what we see in the Milky Way, consistent with early generation stars. Even in these earliest galaxies though, the presence of any heavy elements means stars have already lived and died. Chemical evolution has begun. Webb isn't working alone. The Atacama Large Millimeter Array ALMA in Chile provides complementary observations at millimeter wavelengths. ALMA can detect thermal emission from dust and spectral lines from molecules like carbon monoxide. When Webb identifies a high redshift candidate, ALMA can follow up to search for dust and molecular gas. Several of Webb's early galaxy candidates have been observed with ALMA. Some show dust emission. That's puzzling because dust takes time to form, at least 100 to 200 million years in models. Finding significant dust at 300 million years after the Big Bang means dust production started almost immediately after the first stars formed. Again, the timeline is impossibly compressed. Let's talk about what happens next in terms of telescopes and missions. Webb will continue operating. Each year, new deep fields will be observed. More spectroscopy will be obtained. The census of early galaxies will grow. But Webb is not the only tool coming online. The Nancy Grace Roman Space Telescope, scheduled to launch in late 2026 or early 2027, will complement Webb beautifully. Roman is designed for wide-field surveys, where Webb stares at small patches in incredible detail. Roman will map large areas quickly. That makes Roman ideal for finding rare objects, the most extreme high redshift galaxies, unusual quasars, statistical outliers. Once Roman identifies targets, Webb can follow up with detailed spectroscopy. On the ground, the extremely large telescope, currently under construction in Chile, will have a 39-meter mirror. That's nearly 6 times Webb's diameter, giving it over 30 times the light collecting area. The ELT will work primarily in the near-infrared and visible, not the mid-infrared like Webb, but its enormous size means it can obtain ultra-high-resolution spectra of distant galaxies, revealing details about their internal motions, chemical composition, and structure that Webb can't access. The ELT is expected to begin operations in the late 2020s. Together Webb, Roman, the ELT astronomers will have an unprecedented toolkit for studying the early universe. There are also concepts for future space missions specifically designed to push beyond Webb's capabilities. The Origin Space Telescope and Habitable Exoplanet Observatory are being studied. These would be even larger and more sensitive than Webb, capable of detecting the absolute faintest and most distant objects in the universe. But those missions are decades away if they're funded at all. For now, Webb is humanity's best window into the cosmic dawn, and it's already delivering answers, even if those answers come as new and deeper questions. One of the most exciting prospects is detecting the very first galaxies ever to form, somewhere out there. At redshifts potentially above 20 or even 30, are the galaxies that ended the Dark Ages. The very first stars igniting. The very first structures assembling. The true beginning of cosmic complexity. Those galaxies would be unimaginably faint. Their light has travelled over 13.5 billion years, stretched by expansion into the farthest infrared wavelengths. Webb might be able to detect them, but barely. It would require the deepest exposures ever attempted, hundreds of hours in a single field, and even then, the galaxies might appear as single pixels of light, but that single pixel would represent the edge of the observable universe, the furthest we can ever see. Because beyond a certain point, the universe becomes opaque. Before the first stars formed, space was filled with neutral hydrogen that absorbs light. No telescope, no matter how powerful, can see through that barrier. The first galaxies represent the last observable epoch of cosmic history, and Webb is bringing us closer than we've ever been. Now let's address the question everyone wants answered: what does this mean for life? Galaxy formation and biology aren't directly connected. Galaxies are vast collections of stars, gas and dark matter. Life requires planets, chemistry, and time, but the two questions are linked in a subtle way. If the universe built complex structures immediately, if it moved from simplicity to complexity in a few 100 million years instead of billions, that tells us something profound about the cosmos. It suggests the universe is efficient at organizing matter, efficient at taking raw ingredients and assembling them into structured, ordered systems. That efficiency might extend beyond galaxies. If stars formed rapidly in the early universe, planets might have formed rapidly too. If the first galaxies contained heavy elements within a few 100 million years, the raw materials for rocky planets, carbon, silicon, oxygen, iron, existed far earlier than we thought. And if rocky planets existed early, chemistry could have started early. Life could have started early. Not on Earth. Earth is only 4.5 billion years old. But elsewhere, in a galaxy 13 billion years old, in a solar system that formed when the universe was 1 billion years old, life could have been evolving for 12 billion years. For context, life on Earth has existed for about 3.8 billion years. Multicellular organisms for less than 1 billion. Human civilization for a few thousand. 12 billion years is an almost unimaginable expanse of time for evolution to operate. What could life become in 12 billion years? We don't know, but the possibility exists. Webb's discoveries don't prove life exists elsewhere. They don't make it statistically more likely in any direct sense, but they do reveal that the universe is far more dynamic, far more creative, far more capable of building complexity than we realized. If the universe can assemble 1 billion solar mass galaxy in 300 million years, it can assemble anything. The raw generative power of the cosmos, its ability to take simple physical laws and produce staggering complexity, is greater than we imagined. And that power has been operating for 13.8 billion years. Galaxies, stars, planets, chemistry, biology. Each step builds on the last. Each step Webb is suggesting happens faster than we predicted. The universe doesn't wait, it builds. There's something humbling in realizing that our most sophisticated models, decades of careful theoretical work, can be overturned by a few months of telescope data. Science isn't about being right, it's about being less wrong over time. Every observation that doesn't fit is an opportunity to refine understanding. Webb's galaxies are telling us we were wrong about the early universe. Not completely wrong. The Big Bang happened. Expansion is real. The cosmic microwave background is correctly interpreted, but the details, the timeline, the mechanisms of structure formation need revisiting. And that's not a failure. That's science working exactly as it should. Dr. Emma Curtis Lake of the University of Hertfordshire, part of the JADAS collaboration, described the atmosphere among researchers. This is the most exciting time in my career. Every dataset brings something unexpected. Dr. Sandro Takela of Cambridge echoed that. We built Webb to surprise us. It's doing exactly that. The surprises aren't slowing down as Webb continues operating. As spectroscopic confirmations accumulate, as deeper fields are observed, the picture will sharpen. Some current candidates will be confirmed. Others ruled out. New candidates at even higher redshifts will be found, and with each discovery, the models will be refined, simulations updated, and our understanding of the universe's first billion years brought into clearer focus. What's already clear is the universe didn't waste time. The moment conditions allowed structure to form, structure formed. The moment stars could ignite, galaxies assembled. The universe doesn't build slowly and carefully. It builds explosively, rapidly, with stunning efficiency. And if that's true for galaxies, it might be true for everything else. Chemistry, biology, complexity, intelligence. The universe might be far more alive than we ever imagined. Let's bring this full circle. 13.8 billion years ago, the universe began. For decades, we thought we understood what happened next. Slow, gradual assembly over hundreds of millions to billions of years. The James Webb Space Telescope looked deeper than any instrument before it and found something completely different. Massive galaxies forming within 200 to 400 million years of the Big Bang. Galaxies with billions of stars, organized structures, chemical enrichment that should have taken 1 billion years. galaxies that break Lambda-CDM. The crisis is real. The data is solid. The implications are profound. Either our understanding of gas cooling, star formation, dark matter collapse, or galactic assembly is incomplete, or something fundamental about the cosmological model needs revision. Scientists are working through the possibilities. More efficient star formation, population 3 stars, modified dark matter, faster accretion. None of the solutions are simple. All require pushing physics into unobserved regimes. But the universe doesn't care about our models. It does what it does, and what it did in the first few 100 million years was build galaxies. Massive, luminous, complex galaxies that shouldn't exist yet. The discoveries are ongoing. Webb is still observing. Roman launches soon. The ELT is being built. Every month brings new data, new confirmations, new mysteries. The field of early galaxy formation has transformed from mature and understood to a frontier of open questions in just 2 years. That's what great telescopes do. They don't just answer questions, they reveal how little we knew. Webb has shown us the early universe is stranger, more active, more complex than we imagined. It has forced us to question assumptions we thought were bedrock, and in doing so, it has given us something precious. The gift of wonder. The gift of uncertainty. The gift of knowing there is still so much to discover. For most of human history, the early universe was beyond reach, a theoretical construct, a set of equations. We could calculate what should have happened but never see it. Now we can see it. We can point a telescope at the sky and capture light that's been traveling for over 13 billion years. Light from when the universe was an infant, when the first galaxies were forming, when cosmic history was just beginning. And that light is telling us a story of a universe that doesn't wait, that builds rapidly, that creates complexity immediately, a story that contradicts the one we've been telling. And our willingness to listen, to revise our story when evidence demands it, is what separates science from dogma. One day, perhaps soon, we'll understand how these galaxies formed so quickly. We'll identify the missing physics, we'll refine the models, we'll run simulations that match observations, and when that happens, we'll look back on this as the moment cosmology leaped forward, when a single telescope reshaped our understanding of the universe's first billion years. But until then, we sit with the mystery. We sit with the knowledge that the universe is more capable, more creative, more astonishing than we gave it credit for. We sit with galaxies that shouldn't exist, shining in the darkness, demanding explanation. And we point our telescopes deeper, looking further back, searching for the next impossible thing, because that's what we do. We look up, we ask questions, we build instruments powerful enough to see the invisible, and when the universe answers, even when the answer is everything you thought was wrong, we listen. The galaxies are out there, billions of light years away, billions of years in the past. They formed when they shouldn't have. They shine brighter than they should. They exist in defiance of our best theories. And they are beautiful. Not in the way a sunset is beautiful, in the way truth is beautiful, even uncomfortable truth, especially uncomfortable truth. The story of the universe's first galaxies is still being written. Every observation adds a sentence, every confirmation adds a paragraph. We're not at the end, we're barely past the opening. But what we've learned has changed everything. The universe doesn't follow our rules. It writes its own, and the only way to understand those rules is to keep looking, keep observing, keep questioning. Webb has given us the tools. The galaxies have given us the motivation, and the universe, vast, ancient, full of secrets, is waiting to tell us what happened in the beginning. All we have to do is listen. If you enjoyed this journey into the deepest reaches of cosmic history, hit like and subscribe, because the universe isn't done surprising us, and when the next impossible discovery comes, you'll want to be here. The early galaxies are shining in the darkness, 13 billion years in the past, and for the first time in human history, we can see them, not as we wish they were, as they actually are, massive, ancient, impossible, and undeniably real. But before we can truly understand what these impossible galaxies mean, We need to go deeper into the specific mechanisms that make their existence so troubling, because the problem isn't just that they're early, it's that every aspect of their formation violates multiple physical constraints simultaneously. Let's start with the dark matter halos themselves. In Lambda-CDM, structure formation begins with dark matter. Immediately after the Big Bang, tiny quantum fluctuations in the density of dark matter were stretched to cosmic scales during inflation. Those fluctuations became the seeds of all structure. Regions slightly denser than average had slightly stronger gravity. They pulled in more dark matter. That made them denser still. Positive feedback. Over millions of years, those overdense regions collapsed into gravitationally bound structures called dark matter halos. The size and mass of a dark matter halo at any given time is determined by how long gravity has had to work and how much matter was available in that region. This growth rate is not arbitrary. It's set by the expansion rate of the universe and the strength of gravity itself. You can calculate, given the known properties of dark matter and the observed expansion history, exactly how massive the largest dark matter halos should be at any point in cosmic time. At 300 million years after the Big Bang, the most massive halos predicted by Lambda-CDM should contain roughly 100 million to perhaps a billion solar masses of dark matter. That's the gravitational foundation available for galaxy formation. Now, normal matter hydrogen and helium gas falls into those halos, but not all of it, and not efficiently. As gas falls into a dark matter halo, it heats up. The deeper the gravitational well, the hotter the gas becomes. Hot gas has pressure. Pressure resists further collapse. For a galaxy to form, gas needs to cool enough to lose that pressure support and condense into dense clouds where stars can ignite. The cooling rate depends on which atoms are present. Heavy elements like carbon, oxygen, and nitrogen are excellent coolants. They have many energy levels, so they can absorb and radiate energy efficiently across a wide range of temperatures. Hydrogen and helium, the only elements available in the pristine early universe, are terrible coolants. They have very few energy levels. They radiate slowly. This creates a bottleneck. Gas falls into halos and heats up faster than it can cool down. It sits there, hot and diffuse, unable to collapse further. Only in the most massive halos, where gravity is strongest, does the gas eventually cool enough despite the inefficiency. That's why simulations predict small galaxies form first. Small halos can't cool their gas efficiently. Only large halos can. But large halos take time to grow. At 300 million years, even the largest halos are relatively small, which means even under the most optimistic assumptions, only small amounts of gas should have cooled, condensed, and formed stars. The galaxies Webb found require that billions of solar masses of gas cooled and formed stars. That's not a small discrepancy. That's orders of magnitude more gas, and should have been able to cool in the available time. One proposed solution is that the initial density fluctuations, the seeds of structure, were larger than we thought. If the fluctuations were more pronounced, dark matter halos would grow faster. Faster growth means more massive halos earlier. More massive halos means stronger gravity and more efficient gas cooling. The problem is, we measure those initial fluctuations directly. The cosmic microwave background radiation, the light released 380,000 years after the Big Bang, carries an imprint of those density variations. The Planck satellite mapped them across the entire sky with extraordinary precision. The amplitude of the fluctuations is known. Changing it to fit Webb's galaxies would break the agreement between the CMB and the large-scale structure of the universe we observe today. You'd solve one problem and create 10 others. Another possibility is that gas cooling in the early universe was more efficient than current models assume. Perhaps there were physical processes we haven't accounted for that allowed gas to shed heat faster. One candidate is molecular hydrogen, H-HARC. In the modern universe, molecular hydrogen is rare because ultraviolet radiation from stars breaks it apart. But in the very early universe, before many stars had formed, molecular hydrogen could have been more abundant. H-HARC is a better coolant than atomic hydrogen. It has rotational and vibrational energy levels that allow it to radiate more efficiently. If the first collapsing gas clouds had significant amounts of H-Mercury, they could have cooled faster, allowing stars to form sooner. But there's a catch. forming molecular hydrogen requires specific conditions. You need a dense enough environment for hydrogen atoms to collide and stick together, and you need to shield the H-Martian from radiation that would destroy it. In the chaotic, radiation-filled environment of the early universe, maintaining significant H-Martian abundance is difficult. Models that include H-intra-EK cooling do help. They speed up star formation somewhat, but not enough to explain what Webb sees, not by a factor of 3 or 5. You'd need an order of magnitude improvement. Then there's the question of what happens after the first stars form. Massive stars live fast and die violently. A star 100 times the mass of the Sun burns through its fuel in just a few million years and explodes as a supernova. That explosion releases energy equivalent to the Sun's entire lifetime output compressed into a few seconds. The blast wave heats surrounding gas to millions of degrees and drives it outward at thousands of kilometers per second. This is called supernova feedback, and it's one of the primary mechanisms that regulates star formation in all galaxies. If stars form too rapidly, you quickly build up a population of massive stars. Those stars explode. The explosions heat and expel gas. Star formation shuts down. The system self-regulates. In simulations of galaxy formation, feedback is essential. Without it, simulated galaxies consume all their gas in a single burst of star formation and become far more massive than any real galaxy. With realistic feedback, simulations produce galaxies that match observations in the nearby universe remarkably well. But for the early galaxies Webb found to exist, feedback must have been either much weaker or somehow overcome. If feedback was weaker, why? Supernova physics doesn't change. A massive star exploding 13 billion years ago released the same energy as one exploding today. If feedback was overcome, how? The only way is if gas was falling into the galaxy faster than explosions could expel it. That brings us back to the Eddington limit. When gas falls toward a galaxy and begins forming stars, those stars emit radiation. That radiation exerts pressure on the infalling gas. If the infall rate is too high, if too much gas is trying to collapse at once, radiation pressure becomes strong enough to halt the infall entirely. There's a maximum rate set by the balance between gravity pulling in and radiation pushing out, beyond which accretion cannot proceed. For a galaxy of a given mass, you can calculate that maximum rate. The massive early galaxies Webb found appear to require accretion rates at or beyond the Eddington limit, sustained for hundreds of millions of years. That shouldn't be physically possible, unless something is shielding the gas from radiation. One possibility is that gas isn't falling in smoothly from all directions. Instead, it's streaming in along narrow filaments, cosmic highways of dense gas flowing along the large-scale structure of dark matter. Inside a dense filament, gas can shield itself. The outer layers absorb radiation, allowing the inner layers to continue collapsing. Simulations of structure formation do show filamentary accretion in the early universe, but whether those filaments are dense enough and persistent enough to allow Eddington-violating accretion rates remains uncertain. Some recent models suggest they might be. If true, it could help explain how these galaxies accumulated so much mass so quickly. But it's still speculative. We've never directly observed these early accretion filaments. Another exotic possibility involves primordial black holes. What if, in the very first moments after the Big Bang, tiny fluctuations in density were so extreme in rare locations that they collapsed directly into black holes? These wouldn't be black holes from dying stars. They'd be primordial black holes, formed from the immediate collapse of overdense regions in the first fraction of a second. If such black holes existed and sank to the centers of early dark matter halos, they could have provided gravitational anchors that accelerated galaxy formation. Gas falling toward a black hole heats up and radiates, but some of it gets accreted. The black hole grows. Its stronger gravity pulls in more gas. A massive primordial black hole at the center of an early halo could potentially trigger rapid, efficient star formation in the surrounding gas. This is deeply speculative. We have no direct evidence primordial black holes exist. Searches for them through gravitational effects have come up empty so far, but the gap between observation and theory is large enough that physicists are willing to consider options that would have seemed far-fetched a few years ago. Dr. Priyamvada Natarajan of Yale University an expert on black hole formation, has argued that Webb's discoveries demand we take seriously the possibility of non-standard formation channels for both galaxies and black holes in the early universe. The data is forcing us to think outside the box, she noted in a recent paper. Standard channels may not be enough. Let's talk about another dimension of the problem, the structure of these galaxies. When Hubble observed high redshift galaxies, they looked messy, irregular, clumpy, chaotic. That's what you'd expect for young galaxies still in the process of assembling. Violent star formation, gas clouds colliding, no settled structure yet. Webb's early galaxies, in many cases, don't look like that. Some show organized disk structures, rotating patterns, central concentrations of stars. These are features that develop over time as a galaxy settles dynamically. Stars orbit the galactic center. Through countless interactions, their orbits gradually circularize. A disk forms. The densest regions sink toward the center, building a bulge. This process, called dynamical relaxation, takes time. Hundreds of millions of years at minimum, yet Webb is seeing organized structures at epochs when galaxies should still be in their chaotic assembly phase. How do you build an organized disk galaxy in 300 million years? One possibility is that mergers between smaller protogalaxies happen very rapidly and very early. When two gas-rich galaxies merge, the collision can trigger intense star formation and, under the right conditions, spin up a disk. If many small galaxies formed, merged and settled into disks within the first few 100 million years, that could explain the observed structures. But that requires an extremely high merger rate, far higher than simulations typically predict for that epoch. Another possibility is that the disks aren't as settled as they appear. What looks like a disk in Webb's images might actually be a momentary configuration gas and stars aligned by chance or by a recent merger that will be disrupted by the next interaction. Only deeper, higher resolution imaging and spectroscopy can tell. But even if the structures are temporary, their existence at all is surprising. The universe at 300 million years should be too young, too dynamically hot, for anything resembling organized structure. Yet there it is. There's also the question of metallicity, the abundance of heavy elements. When Webb spectrographs analyzed the light from some of these early galaxies, they found oxygen. Not trace amounts, measurable oxygen abundance. Oxygen is produced inside massive stars through nuclear fusion. When those stars explode, oxygen is scattered into the surrounding gas. The presence of oxygen means at least one generation of stars has already lived and died. At redshift 12, at 370 million years after the Big Bang, we're seeing galaxies that already contain second or third generation stars. How much time does that require? A massive star, say 50 solar masses, lives about 3 million years. It explodes. The oxygen it produced is released into space. That oxygen-enriched gas then has to cool and collapse again to form the next generation of stars. The cooling timescale for gas with some heavy elements is faster than for pristine gas, but it's still tens of millions of years. So you need first generation forms, lives 3 million years, dies. Enriched gas cools over 10 to 30 million years. Second generation forms, minimum timeline 15 to 50 million years between generations. If we're seeing third generation stars at 370 million years and the Dark Ages lasted until about 200 million years, that leaves 170 million years. 170 million years for potentially 2-3 full generations of stellar evolution. It's tight, it's possible. But it requires everything happening at maximum speed with no delays, and some of these galaxies show oxygen abundances approaching 10 to 20% of solar values, higher than you'd expect from just 1 or 2 generations. That implies many cycles of star formation and enrichment compressed into an impossibly short time. Dr. Emma Curtis Lake, analyzing spectroscopic data from JADES, described finding substantial oxygen in a galaxy at redshift 13 as a wake-up call. This galaxy has already undergone significant chemical evolution. The universe barely had time to form stars at all, let alone evolve them through multiple generations. Now let's address what might be the deepest issue of all. If these galaxies are real, if they're as massive as they appear, they represent a significant fraction of all the matter that should exist in their region of space at that time. there's only so much normal matter available. The universe's baryon density, the density of protons and neutrons, the stuff that makes up atoms, is precisely known from the cosmic microwave background at 300 million years after the Big Bang. Given the volume of space and the known baryon density, you can calculate exactly how much matter exists in any given region. The galaxies Webb found appear to have converted an enormous fraction of that available matter into stars. In typical galaxy formation, efficiency is low. Only about 10% of the baryons that fall into a dark matter halo end up in stars. The rest is either still in gas form or was ejected by feedback. To build the galaxies Webb sees, you'd need efficiencies of 50%, 70%, in some cases approaching 100%. That means essentially every baryon in the halo turned into a star. Dr. Boylan-Colchan's simulations highlighted this explicitly. The only way to match Webb's observations in Lambda-CDM is to assume near-perfect baryon-to-star conversion. And that's not just one galaxy, it's dozens. If a significant fraction of early galaxies achieve this efficiency, it has implications for the entire cosmic baryon budget. Where did all those baryons go? They can't have been destroyed. Baryons are conserved. If they're locked up in stars in these early massive galaxies, then other regions of space must have fewer baryons than expected. That could affect the later formation of galaxies, the distribution of matter on large scales, even the properties of the intergalactic medium. It's not clear yet whether this creates contradictions with other observations, but it's attention worth watching. Let's zoom out and think about what all this means for the Lambda-CDM model itself. Lambda-CDM is not a single theory. It's a framework, a set of components that together describe the universe. Lambda refers to the cosmological constant, dark energy, driving accelerated expansion. CDM refers to cold dark matter, providing gravitational scaffolding. Then there are baryons, radiation, neutrinos, and the laws of general relativity governing how it all evolves. The framework has been extraordinarily successful. It explains the cosmic microwave background, the large-scale distribution of galaxies, the abundances of light elements, the accelerating expansion, but Lambda-CDM doesn't predict everything directly. It provides the cosmological backdrop, the expansion history, the growth of dark matter structure, but how baryons behave within that backdrop, how gas cools, how stars form, how feedback operates. Those are subgrid processes, modeled with prescriptions based on our understanding of astrophysics. Those prescriptions have three parameters: cooling rates, star formation efficiencies, feedback strengths. In simulations of the nearby universe, those parameters are tuned to match observations. The tuning worked remarkably well. But when you run the same simulations backward to the early universe with the same parameter choices, they fail to produce what Webb sees. That suggests the problem isn't with the cosmological framework itself, the dark matter, the expansion, the initial conditions. The problem is with the astrophysical prescriptions, star formation, gas cooling. Feedback. Something about how we model those processes breaks down in the extreme conditions of the first few 100 million years. That's actually good news. It means Lambda-CDM itself might survive. But the subgrid physics, the details of how galaxies form, needs major revision. Dr. Sam Bhatt, Rachel Somerville, whose group runs some of the most sophisticated galaxy formation simulations in the world, put it this way: the cosmological model is probably fine. What we got wrong is the astrophysics of how baryons turn into stars in the early universe. And that's fixable. Difficult, but fixable. Fixing it requires new physics, not new fundamental forces or particles, but new understanding of known processes under extreme conditions. How does gas cool when the universe is small, dense, and filled with intense radiation? How do stars form when there are no heavy elements to help the gas fragment into star-sized clumps? How does feedback operate when the first supernovae explode into a denser intergalactic medium? These are questions we couldn't answer before because we'd never observed the early universe directly. Now we can, and every spectrum Webb takes, every galaxy it confirms, is a new constraint on those processes. Over the next few years, theorists will revise their models. They'll include more detailed cooling physics, better treatments of molecular hydrogen, radiative transfer of UV photons, explicit modeling of massive primordial stars. Simulations will be rerun with new assumptions, and slowly, the models will converge towards something that matches what Webb sees. It won't happen overnight. Galaxy formation simulations are extraordinarily complex. Each run can take months on supercomputers, but it will happen. The universe has given us the answer key. Now we have to reverse engineer the equations. In the meantime, observations continue. Every additional deep field Webb observes adds to the census. Every spectroscopic confirmation strengthens the case. And every new discovery refines our understanding of just how extreme the early universe really was. One recent result worth highlighting comes from the JWST Advanced Deep Extragalactic Survey, JADIS. The team identified a galaxy at redshift 14.32, the highest spectroscopically confirmed redshift as of early 2025. That places it just 280 million years after the Big Bang. The spectrum shows hydrogen and oxygen emission lines, clear chemical enrichment, multiple generations of stars already completed. Dr. Brant Robertson, co-lead of JADES, described the confirmation. Every time we think we found the edge, Webb shows us something further. The universe was busy far earlier than we ever imagined. Another striking discovery involves a quasar and actively feeding supermassive black hole at redshift 10. The black hole has a mass exceeding 1 billion solar masses. At just 470 million years after the Big Bang, a black hole that massive shouldn't exist. Growing from a stellar mass seed to 1 billion solar masses in that time requires near-continuous feeding at the Eddington limit. And yet, there it is. These aren't just galaxies anymore, they're entire ecosystems. Massive galaxies with supermassive black holes, complex stellar populations, chemical enrichment, possibly even the beginnings of heavy element-driven dust production. All of it happening in the first 3–5% of cosmic history. The universe didn't slowly wake up. It hit the ground running, and that changes everything about how we think about cosmic evolution, the conditions for complexity, and ultimately, the potential for life. If galaxies, stars, and black holes assembled this quickly, planets could have too. The first rocky planets might have formed within 500 million years of the Big Bang. Chemistry could have started operating on planetary surfaces when the universe was less than 1 billion years old. And if chemistry started that early, biology could have as well. Not on Earth. Earth didn't exist yet, but somewhere, in a galaxy 13 billion years old, orbiting a star in a system that formed when the universe was young, life could have been evolving for over 12 billion years. That's 3 times longer than life has existed on Earth. 3 times as much time for evolution to work. 3 times as much time for complexity to build. What could life become in 12 billion years? We don't know. We can't know. But the possibility is no longer science fiction. It's a reasonable extrapolation from what Webb has shown us about how quickly the universe builds complexity. The cosmos is efficient. It's fast. It doesn't waste time. And if it built galaxies in 200 million years, it can build anything. Now we wait. Webb continues observing. Roman will launch. The ELT will come online. Each new instrument will push deeper, see fainter, resolve more detail. Spectroscopic confirmations will accumulate. The census of early galaxies will grow from dozens to hundreds to thousands. And slowly, the theoretical models will catch up. We'll understand how gas cooled so efficiently. We'll identify which feedback mechanisms were weaker or absent. We'll pinpoint how star formation proceeded so rapidly. The mystery will be solved, but the wonder will remain. Because even when we understand how it happened, the fact that it did that the universe exploded into complexity almost immediately will still be astonishing. The cosmos is not patient. It is not slow. It is an engine of creativity running at maximum speed from the very beginning. And we are only now, 13.8 billion years later, beginning to see what it built. The galaxies are out there, shining in the ancient darkness. Impossible, beautiful, waiting for us to understand them.